Hello everyone. In this video, we are going to discuss the hand of straights problem. In this problem, we are given a list of numbers which represents a deck of cards. We are also given an integer called n. Our goal is to find out if it is possible to use all the cards in our deck to form groups of consecutive cards of size n. A consecutive cards group is a group of cards that can be arranged such that they increase by 1 from start to finish. If you have played poker before, this is similar to a hand known as a straight, but in this problem, the straight doesn't have to be 5 cards, but rather n cards. So for example, if we are given this list for our cards and n is 4, we would return true because we can arrange the cards into 2 groups. Group 1 would have the consecutive numbers 1, 2, 3, 4, and Group 2 would have the numbers 3, 4, 5, and 6. If instead we were given this arrangement on the right here, we would return false because while we can use 1, 2, and 3 to form a consecutive group of size 3, we can't fit that 5 to make this a size 4 group, which is what we are going for because obviously the gap between 3 and 5 makes this group not consecutive. The other thing to note is that we must use all the cards. So say in this example in the bottom left, we have n equals 5. So we are looking to form groups of size 5. We can use the first 10 cards to form 2 groups of size 5. However, there is one leftover number, the 9, and since we aren't able to use that number, we still have to return false. So if we want to return true, at the very minimum, the amount of cards we are given has to be divisible by n. That can actually be a check in the very first part of our code. If the size of the cards list is not divisible by n, then we know, regardless of the values of the cards, we are never going to be able to use all the cards to form groups of size n, so we can just return false immediately. Now that that is out of the way, let's start to think of how we can come up with a solution. One of the key realizations I had to make when solving this problem was that if there is a valid way to arrange the cards, that arrangement is going to be the only valid arrangement. So for example, this arrangement of cards, there is a valid arrangement which I've shown here, and this valid arrangement is the only valid arrangement. Yes, we can swap numbers that are the same, like you could swap the 2 3s or the 2 4s, but that is still the same arrangement. This fact is useful in developing a solution because it allows us to develop a greedy approach. That greedy approach is that we can start from the smallest card, let's say the value of this card is x, and we know that if there is a valid arrangement, this smallest card is going to have to be paired with the next x plus n minus 1 cards. So if we say, for example, our smallest card is 3 and n is 5, then we know this 3 card has to be in a group with the values 3, 4, 5, 6, and 7. This has to be the case because the only other situation would be that x is in the middle or the end of a group. Something like this, where x is 3, but it is in the middle of a group where there is 1 and 2 in front of it. But the problem here is that this is a contradiction because we said that x was the smallest card. Since 1 and 2 are present, then x is actually not our smallest card, 1 is our smallest card. So now if we take a step back and try to develop our solution a bit more, we know that if we have some card x, and we know that this is the smallest card, then we know that it has to be part of a group from x to x plus n minus 1. So our solution can be to process the cards in increasing order. Anytime there is a card available, since we are processing in increasing order, then we know that this is the smallest card currently that can be used for a group. We then attempt to try and form a group with this card and the next n-1 cards, and if we can form a group, we continue on to find the next smallest card that isn't part of a group yet. If we make it to the end of the algorithm and all the cards have gone into groups, then we return true. If this is a bit confusing, don't worry, let me demonstrate the strategy. So let's say these are our cards and that n is 3, which means we are trying to form groups of size 3. The first thing to do is to sort the cards. Next, we start with the smallest number, which is the 1. So for the 1, we check if we can form a group of size 3 with it. So a group of 1, 2, and 3. We can obviously pull these 3 cards, and this will be our first group. Now we repeat the process for the next smallest number that is not in a group. That number is the 2. Once again, we check and see if we can form a group with 2. That group would look like 2, 3, and 4. We can, so we move these 3 cards into their own group, and now we have 2 groups. Next, we move on to the next smallest number available. This is the 7. We repeat this process and look to see if 8 and 9 are present and not in a group yet. They are, so we once again have these cards go into their own group. Since we have successfully grouped every card, we can return true. If earlier in our algorithm at any point we could not find a card to form a group, then we would have returned false. So for example here, while we were looking at this 2, we would be looking for a 3 and a 4, but instead of a 4 being present, that card happened to be a 5, we could no longer form a group, and we would just break out and return false. So now that you hopefully have a high-level understanding of our solution, let's get into the code. This is where we left off. Those first 2 lines were a pre-check to see if the amount of cards was divisible by n. As we just discussed, we need to know how many of each card number there are so that we can check if a card has been put in a group or not. This means in our code, we are going to build a frequency hash map. This hash map is going to have its keys be the card numbers and its values be the number of cards that still have not been grouped for that card number. The code here is pretty straightforward. For every card in the deck of cards, if the card is already a key in the frequency map, then we can just increment the frequency by 1. Otherwise, we create a new entry and set it to 1. The second part of our algorithm is the greedy part, where we iterated through the cards in sorted order. In order to do this, we sort the keys in the map, and in Python we can use the sorted function to do this. While there are still cards available for this number, we decrement this frequency to symbolize us placing this card in its own group. Then we try and look for cards that are of the value key plus 1 to key plus n minus 1. This part of the code corresponds to us picking the lowest number and then trying to see if the range of cards from this number to this number plus n minus 1 are available. So in our code, if I is not present or its frequency is 0, it means there are no more cards of this value available for grouping. If that is the case, we know that we can't form a group with this card. And that means we can stop early and return false. Remember, we can do this because of the greedy argument that I made earlier. That if we can't find the next n-1 consecutive greater cards, it means that this card is never going to fit into a grouping, and if this card is never going to fit into a grouping, then there isn't going to be a valid grouping overall. On the other hand, in our else statement, if there still is a card available, we use it and put it into a group. We symbolize this by subtracting 1 from the frequency. And finally, if we make it to the end of the algorithm, it means we have successfully placed all the cards into groups, so we can return true. Okay, that is it for the code. The last thing for us to do is to analyze the time and space complexity. For time, the most costly step is the sorting of the keys. Since I've already used n as a variable in this problem, let's use a to represent the length of the list. So because of the sort, the time complexity is going to be a log a. One thing to point out is that this inner for loop in the while loop is not quadratic complexity. The reason for this is that every time the inner loop runs, one card is subtracted from this frequency, or we return. This means that these loops only run for a total of the amount of the cards in the deck over the course of the entire algorithm. The total amount of cards is obviously just a, so that part of the algorithm is O of a, despite the fact that we have deceptively deep nesting. For space, the only additional space we are using is the frequency map. That can grow to size a, so our space complexity is O of a. Okay, now that we have discussed the time and space for this solution, let's try and improve the time complexity. As with a lot of other problems, a good starting point when we are trying to improve our solution is to look at what is costing us time. For this problem, that is the a log a that comes from when we are sorting the cards. So in order for us to improve, we need to develop a solution that does not need to sort the cards. One thing to realize when trying to develop this second solution is that for every deck of cards, it is going to be composed of some number of consecutive card groups. So for example here, for this deck, we have 3 groups of consecutive numbers. Each of these separate groups needs to be able to form n-size groups themselves, otherwise we can't form a valid grouping for our overall answer. You can see group 1 form its own group of size 3. Group 2 can be further divided to form 3 groups of size 3, and group 3 forms a group of its own. So like I said earlier, each of these subgroups needs to be able to form consecutive groups of size n themselves for our final answer to be true. The second thing is that we don't need to process any of these groups in any particular order. So I could determine if group 3 can form valid groups, then group 1, then group 2, or any order I want, it doesn't matter. And it's this realization that allows us to avoid sorting the entire deck of cards. At this point, you might be a bit confused, so let me get into more details and try to explain this by demonstrating how our algorithm is going to work. So let's use this example. Our solution would start by picking any card in our card deck at random. It doesn't matter which one. So for example, let's just go with one of the 9s. Now we need to determine what is the smallest number for the subgroup of consecutive cards that this 9 is a part of. So to do this, we count down the numbers and ask if this number -1 is in our deck. So for the 9, we ask if there is an 8 in our deck. There is, so now we look for a 7. A 7 also exists. So now we look for a 6. That also exists. So we look for a 5, and now there's not a 5. So that means for this consecutive subgroup that the 9 is part of, the 6 is the lowest number. Now that we know the lowest number, we just apply the same algorithm from our first solution. So from the 6, we look for the 6, 7, and 8. These numbers are present, so we use them to form their own group. So now we continue on with the next smallest number in this subgroup, which is the 8. For the 8, we check if there's an 8, 9, and 10, and there are, so we pull those numbers into their own group. The next smallest number is a 9, so we look for 9, 10, and 11, which are all present, so we pull those 3 into their own groups. And that completes this subgroup of consecutive numbers. Once we are done processing a subgroup, like we did here for these 6 through 11, we repeat the process by once again randomly choosing any of the cards that are remaining. And I'm not going to continue walking through that because I feel like it would be redundant. So let's actually get into the code now. So the code is a bit longer and might be difficult to understand if I just incrementally show it. So I'm just going to paste the whole solution here, and then I'll step through it to explain each piece. If you want, you can pause the video and try to understand it yourself without my commentary, and then just skip to the time complexity at the end. But anyway, let's dig into it. On the right, we have the main function, and on the left, we have 2 helper functions that the main function calls. First, we have a call to the build frequency map helper function. This is the same as the first solution, building up the frequency map. I've just moved it into its own function, but it does the same thing. Next, we have a while loop, which runs while there are still elements present in the frequency map. In our while loop, we choose any random card from the frequency map. I couldn't really find any non-hacky way to do this in Python, so I decided to just do this with 2 lines of code here. The first pops a random element from the map and records the card number and frequency, and the second line just puts the popped value back into the map. Now we need to find the smallest card of the consecutive subgroup that this chosen card is a part of. We do this with a variable called smallest, and while there is a card that is 1 smaller present in the subgroup, we continue to decrement this variable. Once we have identified the smallest card in the subgroup, we call our second helper function called process subgroup. This second helper function on the left is very similar to the first solution we came up with earlier in the video. First, we have an array called subgroup. This is going to be an array of tuple pairs, where the first number in the tuple is going to be the value of the card, and the second number is going to be the frequency of the card. We're going to use a variable called card to iterate through our frequency map and move the cards in this consecutive subgroup from the frequency map into the subgroup variable. This variable starts off at the smallest because that is the first number we are going to move. So while this card is in the frequency map, we pop this card from the map. What pop does in Python is it deletes the key value entry in the map for the key you pass in. In this case, the key I'm passing in is the card. It returns the value of that key prior to deleting it. In our case, the value is the frequency, and I've stored this return value in a variable called count. We then append this card value and frequency count as a pair into our subgroup list. And finally, we increment the card value to repeat this process for the next card in this consecutive card group if there is one. Now the next part of the for loop is also very similar to the first solution. It is just this time, instead of working with the entire sorted frequency map, we are working with the list of tuples that we have built up for this consecutive subgroup. Let me actually paste this first solution from earlier on the right here, and I think that will make it a bit easier to understand this portion of the solution. So we iterate through every element in the subgroup array. Remember that we store the frequency in the second position, or index 1, so while subgroup's i's frequency is greater than 0, we subtract 1 from the frequency because we are using this card to form a n-sized pair. We then try to group this card at the ith position with the next n-1 cards greater than this card. If either we are out of bounds or the frequency of the card we are looking for is less than 1, which means it's 0, we can't form a grouping, so we can exit out and return false immediately. Otherwise, we subtract 1 from the frequency to add that card to the grouping. Finally, if we make it to the end of the for loop without returning false, it means that all cards in this subgroup have been paired, so we return true. Once again, let me point out how similar this part of the solution is to our first solution. So if you're having some trouble understanding this part, it might be helpful to reference that first solution on the right. But now that I've traced through the helper function, let me replace the code on the right with our second solution again. So now back to our main function. We store the result of the function called to the helper function into a variable, and if that result is false, it means we aren't able to form a grouping for this subgroup, which means we're never going to be able to form a grouping for the entire deck, so we can break out and return false. Ultimately though, if all the subgroups are able to form valid groupings, then we know that we can form a valid grouping for the entire deck, so we can return true. Okay, that's it for the code walkthrough. Let's analyze the time and space complexity. Once again, we're going to let A represent the amount of cards in the deck. For time, we have improved from A log A in our last solution to O of A. You might be a bit skeptical of this given all the while loops, but let's analyze the runtime of these while loops from an amortized perspective. First, we have this while loop, which is O of A because it runs while there are still elements in the frequency map. Worst case, one element gets removed at a time, so that is O of A. Next, we have this inner while loop. This counts down from the randomly chosen card to the smallest card in the consecutive subgroup. This is worst case O of A. However, the reason that the nesting doesn't cause the time complexity to go up to O of A squared is that this while loop can only run once per card. The reason for that is either the algorithm is able to find a successful grouping for this subgroup, or it's not able to. If it's able to, then all the cards in this subgroup are removed, which means that on subsequent iterations, this while loop will never touch the card again. If there's no successful grouping, then this algorithm will exit early with false, so we don't have to worry about it either. Next, we go inside the process subgroup helper function. Once again, despite the fact that this loop is nested, it does not bump up the time complexity to quadratic. If you look at the first while loop inside the process helper function, it iterates through the frequency map, which can be of size A. However, For every element it iterates over, it pops that element from the frequency map. So on subsequent calls to this function, we will never reiterate over the same card with this loop because it has already been deleted. So once again, we can conclude that each card can only be iterated over once over the span of the entire solution, which means that the time complexity over the course of the entire solution is O of A. And for this next for loop, it's the exact same thinking. I've actually already explained why each card will only be iterated over once in the first solution, so I don't really need to repeat myself, but I would recommend you pause the video here and verify for yourself why, despite all these nested loops, our time complexity is still worst case O of A. So for time, that linear runtime is a good improvement. For space, unfortunately, it stays the same at O of A. The two major spots that use extra space are the frequency map and the subgroup array and the helper function. Both of these can grow to size A, so that is our space complexity. Okay, now that we have discussed the time and space for this second solution, that is actually the fastest solution that I could come up with, so that's it for this video. To recap, we first came up with an A log A solution, which involved sorting. Then we built on that idea to come up with this solution here, which is an improvement to linear time. Anyways, as always, thank you for watching. I hope you found this video useful, and good luck on all your interviews.